Good morning. Truth value of a qualified quantified statement. The following rules are employed for determining the truth value of a quantified statement. Rule 1. Here we have 2 points. In the first point, for all x belongs to S is there. In the second point also, for all x belongs to S. But here P of x is true, here P of x is false. The statement is true if it is true for all points of x belongs to S. If the statement is false, it is enough to show that there exists one element A belongs to S such that P of A is false. This is rule 1. Next, we move on to rule 2. Here, observe there exists X belongs to S. There exists X belongs to S. Here, P of X is false. Here, P of X is true. P of x is false and a symbol is there exist, then P of x is false for each x belongs to S. So observe rule 1 and rule 2 are reverse. Here false means it is false for everywhere. Here true means it is true for everywhere, but the symbols are here for all. Here there exist. P of x is true if it is enough to exhibit one element A belongs to S such that P of A is true. So, whenever for all symbol is there and the statement is true, P of x is true, then it is true for all points of S. And also for all is there, statement is P of x, statement is false means the statement is false at any one point A belongs to S. Now there exists P of x is false means it is false for every x belongs to S. There exists, symbol is there exists, P of x is true, then it is true for at least one A belongs to S. So, these two are, so here true is there for all x belongs to S. Here false is there for all x belongs to S. Here false is there, A belongs to S. Here true is there for A belongs to S. So example 1 for rule 1. So observe first one. Here x is a real number. We know that real number is the union of natural number, whole numbers, integers, irrational numbers and quotient numbers. So x is a real number. X square I am going to finding this x square is always greater than or equal to 0. So this x square is true for any real number. For example, I am taking 1. 1 is a natural number. 1 square is equal to 1. That is greater than 0. Whole number. I am taking 0 as whole number. 0 square is 0. 0 equal to 0. Next I am taking positive integer, that is t. 3. 3 belongs to z. Z plus 3 square equal to 9. 9 is also greater than 0. Now I am taking minus 3, that is negative integer. Minus 3 whole square, we know that 9. 9 is always greater than 0. So irrational numbers. Next I am taking root 2. Root 2 is an example for irrational number. Root 2 whole square is 2. 2 is also greater than 0. Next I am taking quotient number. that is 2 by 3. 2 by 3 whole square is 4 by 9. 4 by 9 is always greater than 0. That means if I take any real number, the value of x square is always greater than or equal to 0. Next, we move on to second example. So observe, here also I am taking real number system and x is greater than 0. This is false. False means if it is false at a single point is also okay. So observe, here I am taking real number system. Real number system means positive integers are there, negative integers are also there. If x equal to minus 1 is not greater than 0. Minus 1 is always less than 0. That's why when the statement is false, it is enough to show that it is false at a single point. Next, move on to rule number 2. So observe rule number 2. Here the symbol is there exist. X is a real number. Already you know the real number system. Here x square equal to 9 is there. So whenever we get 9 as answer means there is only two possibilities. One is 3 square, that is 9. Minus 3 whole square is also 9. That means the statement is true only when x equal to 3, x equal to minus 3. Again, there exists x belongs to R such that x square equal to minus 1. This is false because no real number satisfies this. Observe, I am taking here also positive integer 2 square, that is 4. 4 not equal to minus 1. Negative integer minus 4 whole square, that is 16, also not equal to minus 1. That means we cannot find any x, that is any real number satisfying this condition. So these are the examples of rule 1 and rule 2. Next, we are move on to examples of universal quantifiers. These are the examples of universal quantifier. Let us observe here P of x denotes x is an undergraduate student. The statement P of x means x is undergraduate student. Here U is the set of all enrolled students. That means U means the students, the BSc students, BCA students, BBA students and also BA students. So U means it is the union of total combinations of college. So if the student is BSc student, then he is also undergraduate student. If the student is BCA student, then he is also undergraduate student. If the student is BBA student, then he is also undergraduate student. If the student is BA, then he is also undergraduate student. That means P of x is always true. This is an example for universal quantifiers. Universal quantifiers means those are all true for every value of x. Move on to next example. If P of x denotes x greater than 0. So P of x is x greater than 0. U is set of integers. Set of integers means minus 3, minus 2, minus 1, 0, 1, 2, 3 like that. So these are negative integers, these are positive integers. These are negative integers, these are positive integers. So observe, if I am taking minus 3 is greater than 0, false. If we get 1 like this, then we can say that P of x is false because here we have for all x. Third example, observe the same thing, x greater than 0, x greater than 0. But here we are taking integers, here we are taking positive integers. So these will go. And also 0 is not comes under positive integers or negative integers. So 1, 2, 3 is there. Observe 1. If I take x as 1, x greater than 0, 2 greater than 0, 3 greater than 0. That means always x greater than 0 if we take u as positive integers. That's why P of x is true. Here for all x is there. Whenever for all x is there, P of x is true for every point of that set u. Next, fourth example. If P of x denotes x is even, u is integers. Here also we are taking u as integers only. Even number means a number which is written like this, 2n. Observe, if x is minus 3, we cannot write minus 3 as 2 into something. That means this statement is false when we take u is an integer. If the statement is false at a single point, then the statement totally false because here for all x is there. Fifth example, if P of x denotes x is mortal and u represents all human beings. So all human beings are mortals. That means for all human beings, P of x is true. So finally, I concluding, if for all x is there, the statement is true if it is true for all values. For all x is there, if the statement is fails at a single point, then the statement is false. We consider the statement is false only. So next we move on to the next question. What is the truth value of the quantification for all x? Where P of x So next question. What is the truth value of the quantification for all x, P of x, where first question, P of x is the statement x less than 5 and universe of discourse consists of real numbers. So observe, here x is less than 5. So this is the statement. We want to take x as a real number. X belongs to R. Observe, real numbers means it is negative integer, positive integer, fractions, irrational numbers, all those. If we take root 2, the value of root 2 is 1.4 something. This is less than 5. If I take negative integer, minus 1 is less than 5. If we take 1, it is also less than 5. 2 less than 5, 3 less than 5, 4 is also less than 5. When we take x as 5, 5 equal to 5. At this situation, this statement is false. And also if we take x as 6, 6 is less than 5. Here also the statement is false. If the statement is false at a single point, then we say that the total statement is false because here we have for all x. Next we move on to B question. P of x is the statement P of x is the statement x square less than 18. And the universe of discourse consists of positive numbers not exceeding 5. So positive integers not exceeding 5 means we get 1, 2, 3, 4. Once we check, 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16. Observe, 1 is less than 18, 4 is less than 18, 9 is less than 18, 16 is also less than 18. That means this statement is true when we take x equal to 1, 2, 3, 4. That means that statement is true for all these values. So it is conjunction. Conjunction means and. So observe, 5 square is, and also here 5 square we have taken, that is 25. 25 is greater than 18. So in this case it is false. That's why the statement is false. Not exceeding 5 means we want to take 5 also. Next, examples of essential quantifiers, existential quantifiers. Observe, P of x here denotes x is a creative student. U is set of all enrolled students in BCA 2022. Among these, are some students is creative. At least one we get some creative student. That means P of x is true. Here observe, there exist is there. If one is true means total statement is true. If P of x denotes x equal to x plus 1 and u is integers, here there exist is there, P of x is false. Why means we can't find any x that is equal to x plus 1. Next, third example, P of x denotes x equal to x star 2. Here also we can't find any x such that x equal to 2x. That's why the given statement is here also false. So observe next example, P of x denotes x is a friend of Mickey Mouse and U is the cartoon character. So Mickey Mouse is a cartoon character. That means X is a friend of Mickey Mouse. So at least, so Mickey Mouse is a cartoon character. U is cartoon character set only. That's why there exists at least one P of X is true. Why this statement is true means Mickey Mouse is a cartoon character. Next example, what is the truth value of the quantification for all x, P of x, where P of x is the statement x greater than 5 and the universe of discourse consists of real numbers. So this is also same thing we can do. Here x is a real number. If we take x equal to 6, 7, 8 dash dash, at least 1 means okay. Here 6 is there, 6 is greater than 5. We find one x such that x is greater than 5. That's why this is true. 7 is also greater than 5. 1 is enough. That's why I explained by taking 6 only. Next one, P of x is a statement x square greater than 18 and the universe of discourse consists of positive integers not exceeding 5. So here I am taking, in the previous example, I am taking conjunction, but there we have for all x. Here there exist. That's why here I am taking disjunction. Disjunction of P of 1, P of 2, P of 3, P of 4, P of 5. Here P of 5 is true. That is 25 is greater than 18. That's why if 1 exists means okay. Therefore the total statement is true. For here there exists x is there. That's why P of x is true. So next we move on to another example. Here P consists of 2, 3, 4, 5, 6. State the truth values of each statement. So first we do this one. So X is an element of this set. X plus 3 less than 10. So first I am taking X as 3. 2 plus 3 is 5. 5 less than 10. Next I am taking 3. 3 plus 3 is 6. 6 is also less than 10. 4 plus 3, that is 7. 7 is also less than 10. 5 plus 3, that is 8. 8 is also less than 10. 6 plus 3, that is 9. That is also less than 10. That means if I take any number in the set P, the statement is true. That's why the final statement is true. For all is there, at all points it is true. That's why the statement is true. Next we move on to next one, that is for all x belongs to P, x plus 2 is less than or equal to 7. So here I want to add each element with 2 and observe whether it is less than or equal to 7. So here it is false. Y means when we take x as 6, 6 plus 2 is 8. 8 is not less than 7 and also not equal to 7. If we find one point where the statement is false, here for all is there, that's why total statement is false only. Here next there exists x, the statement is x plus 3 equal to 10. This here I've written false. Y means for no number in P is a solution x equal to x plus 3 equal to 10. That means solution means x plus 3 equal to 10 means x equal to 10 minus 3. 10 minus 3 is 7, but 7 does not belongs to P. That's why the statement is false. There exists x such that x plus 2 less than 7. This is true because we are going to find one x, that means x plus 2 equal to 4. 4 is less than 7. Finally, I am telling for all x belong for if for all is there, the statement is true in all cases. If for all is there, if the statement is failed and at a single point, then the statement is fail only. If there exist is there, if the statement is false, if the statement is false at a single point, then it is false only. If there exist is there, if we find the statement is true at a single point, then it is true only. So, the second video completed.